5.2, we're going to look at explicit formula, specifically for an arithmetic sequence. So this link will be on Google Classroom, and we're going to work through these slides together. So the first one is the warm-up. Consider the sequence -4, -2, 0, 2, 4, 6, 8. Is this arithmetic or geometric, and how do you know? So in class, I'll give you time, and you'll select arithmetic or geometric, and then you'll explain how you know. So once you choose one, I'll ask you to explain your thinking. I would choose arithmetic. And the reason is, if it's arithmetic, there's this common difference here, something that we add to every term to find the next term. So if I take -4 plus 2, I'll get -2. -2 plus 2 is 0. 0 plus 2 is 2, and so on. Since I'm adding the same thing every time, it's arithmetic. So we're going to go over some different definitions today, and you can add any of these to your math notebook, to your notes, if you think it's going to be beneficial to do that. So first is a sequence. In a sequence, we're going to look at something called a common difference. So recall that a sequence is an ordered list of numbers, and an arithmetic sequence is made by adding the same value every time. And the number that you add can be positive or negative. So instead of subtracting, we do say we're adding a negative number. So we're adding terms to find the next term. And again, it can be a positive or negative number that we're adding. And that number that we're adding every time is called a common difference, or D. So that is something that you'll have to know. I might say find the common difference, and that is just the number that we add every time to find the next number in the list. And again, this list of terms is called a sequence. So here's an example of a question that I might give you. Find the common difference for D, or find the common difference D for the following sequence. So we have 1.4, 2.6, 3.8, 5, and 6.2. So what I'm asking you to find is, what number are we adding every time to get the next number? And what is an easy way to find that? Well, an easy way to find that is to take any number except for the first number in the list. And instead of adding, we can go backwards and subtract the number before it. And that will give us the common difference. So for example, if I take 6.2 and I subtract the 5, I'm going to get 1.2. And that should happen every time. If this is truly arithmetic, we should get that difference of 1.2 every time. So I could take 5 minus 3.8, and I get 1.2. I can take 2.6 minus the 1.4, and again I get 1.2. So here our common difference is 1.2, because that's the number we would add every time to find the next term. And if we didn't know what the common difference is, we can go backwards and we can take any number and subtract the number before it to find the common difference. A geometric sequence is formed by multiplying the same value every time. And again, this can include multiplying by a fraction. We multiply it by a fraction instead of dividing. So an example of that is, I might give you the sequence that is 8, 4, 2, 1, and so on. And to get from one term to the other, instead of saying you can divide by 2, which we see that you can divide by 2 here. So 8 divided by 2 is 4, 4 divided by 2 is 2, and so on. You think, what do you multiply by? And if we multiply by 1/2, we'll get the same answer as instead of saying divide by 2. So a common ratio is what you multiply by every time. And you can think of it in terms of multiply and divide, but here, multiply. And again, to find the common ratio, how can we easily find it? It's kind of like what we did before. You can take any number and divide by the one before it. So 1 divided by 2 is 1/2, 2 divided by 4 is 1/2, 4 divided by 8 is 1/2. So to find the common ratio, you just take any number and divide by the number before it, and it will give you the common ratio. So let's find the common ratio for this sequence. Again, if we don't know what it is, we can take any number and divide by the number before it. So if I take 11.2 and divide by 5.6, I'm going to get 2. Oops, I popped up my calculator here. If I take 5.6 divided by 2.8, again, I'm going to get 2. And if I take 2.8 divided by 1.4, I will get 2. So here the common ratio is 2. If you multiply by 2, you get the next number in the list. And again, an easy way to find the ratio is to take any number and divide by the number before it. Okay. So terms, I've been using this word terms. Each number in your sequence is a term. We use a sub 1 to stand for the first term. Sub because it's a subscript. So a sub 1 is how you read it, and that means the first term. A sub 2 is the second term, and so on. Find a sub 6 in the sequence below. So when I say find a sub 6, I mean, what is the sixth number in this list? So again, the first number, a sub 1, is 800. The second number, a sub 2, is 400. The third number, a sub 3, is 200, and so on. And we have to look for the rule. So first of all, is this arithmetic or geometric? And if you notice, we're dividing by 2, or negative 2, I should say, every time. And that's the same as multiplying by 1/2. So again, to find the ratio, and let me write this sequence up. So we have 800, negative 400, 200, negative 100. Okay, so I wrote up the sequence. Oops, here's my calculator. And to find the ratio, you pick any number, so I'll just pick negative 100, and divide by the number before it, and I'll reduce the fraction. So instead of saying multiply by instead of saying divide by negative 2 every time, the ratio is asking, what are you multiplying by every time? So here we're multiplying by negative 1/2 every time to get the next term in the sequence. So again, the ratio is what you multiply by. To get it, you take any number and divide by the number before it. So here, we want the sixth number in the list. So I can actually program my calculator to do that. So I will type in the first number, and then I'm just going to multiply it by negative 0.5 or negative 1/2 every time. So now every time I hit enter, it's multiplying by, so there's the first number in the list is 800. Negative 400 is the second term. 200 is the third term. Here's the fourth term, fifth, and sixth. So we can see our sixth term is negative 25. Oops. So a sub 6. And if you want to write a sub 6, I can type a and then I'll do the shift underscore or shift dash, and there's underscore. So a sub 6 is negative 25. You could also just say negative 25. And this is geometric because we're multiplying by negative 1/2 every time. And and the reason is we're multiplying by negative 1/2 every time. Okay, another kind of hint to when you're looking at a list of numbers is if it alternates from positive to negative, it's not going to be arithmetic. It has to be geometric because a negative times a negative is a positive. So when I'm asking you, is this arithmetic or geometric, and you see positive, negative, it's going to be geometric or neither. Okay, so let's take a look at stadium seating. So let's say we have a stadium with 75 rows, and it has 10 seats in the first row, 15 in the second row, 20 in the third row, and so on. If I were to ask you to find a sub 6 in this situation, what am I asking you to find? And a sub 6 means the number of seats in the sixth row. And now if we find a sub 6, again, if I'm listing this out, so here's my scratch paper here. In my first row, we have 10 seats. So there's the first row. In the second row, we have 15 seats and 20 in the third row. So it goes 15, 20. And we want to know, okay, this is increasing. What is it increasing by? Are we adding or multiplying? And here we can see we're clearly adding by 5 every time. But if you didn't know, you could take 20 minus 15, get 5. 15 minus 10, get 5. So we can see that we're adding 5 every time. And again, we want the sixth row. So here's a sub 4, a sub 5, a sub 6. So I can just keep adding 25, 30, 35. So in the sixth row, there's 35 seats because we're just adding 5 every time. So again, you can say a sub 6, a and then the underscore 6 equals, 35 seats. You could say just 35, and that would be fine. All right. Complete the table below. So this is that same problem that we had before where we're adding 5 every time. So in the first row, there's 10 seats, then there's 15, then there's 20, 25, 30, and 35. Okay, so there's what the graph looks like. And keep in mind that x is the row number, so in row 1, there's 10 seats. Seats is the dependent variable because whatever row there is, the number of seats depends on that. So then, when we graph the stadium seats data, what does our data appear to look like? Is it linear? Is it exponential? Is it quadratic? And we can see that it's a pretty straight line. We have the slope right here, the slope of 5 every time. So this is linear. If our data is linear, we can model it by the equation y equals mx plus b. What does m stand for, which is next to the x? What does b stand for? And we know that m is the slope because it's next to the x. And b is the y-intercept, or the starting value. And if we notice on our graph here, we don't have the y-intercept. We just have like row 1. But we could go backwards. If we could figure out the y-intercept, we could go backwards and get that our y-intercept would be 5. So if I were to graph that, we could say, all right, y equals, it's going up by 5 every time. But in the row 0, if there was a row 0, there would be 5 seats. Because in row 1, there were 10. So in a sequence of numbers, I forgot us here. In the sequence of number of chairs per row, 10, 15, 20, the first term is 10. The second term was 15. The third term was 20. In order to use y equals mx plus b, we would need the 0 term, or the y-intercept. And we can get this by shifting the equation back one term to get the 0 term. And so instead of using y equals mx plus b, there's another equation that we can use. We can start with the first row. We can add 5 every time, which is d, the common difference. But the n minus 1 will shift this back so that we are actually starting at row 0 instead of row 1. So that's what the n minus 1 does. It shifts it so that we're actually starting at the y-intercept and not at term 1. So all of these stand for something. N is the term number. A sub 1 then would mean the first term. And d is the common difference. So let's choose the correct explicit formula for the stadium problem. So first term is 10. So we're looking for which one has first term of 10. And it could be this one, or this one. And then what is it doing? It's going up by 5 every time, and that's the common difference. So it has to be this one right here. So we're starting at 10 rows. Okay, so first term, a sub 1. I want to use a sub 1. I have to use this equation tool. Equals 10, so we plug that in. And the common difference is positive 5. So it would be this third equation right here where we start with 10 and we're adding 5 every time. Again, the n minus 1 just shifts it so it goes back to like row 0, which is where we're going to start at. Okay. Let's evaluate the explicit formula. It says from the previous slide, we know that this is the right answer. Muna says that the correct equation can also be written as 5 plus 5n. Is she correct? Why or why not? So I'm going to write this down and let's see, are these equivalent equations? Okay, so here's the equation that we're going to start with. Let's simplify it. Let's distribute and combine like terms. So you have 10 plus 5n, and then 5 times negative 1 is negative 5. So I just distributed it and multiplied. 5 times n is 5n. 5 times negative 1 is negative 5. Let's combine like terms. And 10 minus 5 is 5 plus 5n. And so this is actually an equivalent formula. And another way even to write it, if we're talking about y equals mx plus b, we can see that our slope is 5. And we could see that if there was a row 0, there would be 5 seats in that row because row 1 starts with 10 seats. And so if we go backwards, we can subtract 5 seats, and we would have 5 seats in row 0 if there was a row 0. So there's actually many ways to write that equation, and so Muna is correct. She can distribute and simplify the equation, and she'll get 5 plus 5n, or 5n plus 5. So yes, she is correct. If you distribute, we get her equation. Okay, so why do we need the explicit formula? It says a stadium with 75 rows. Okay, so here's the original problem. 10 seats in row 1, 15 seats in row 2, 20 seats in row 3, and so on. If I ask you to find a sub 30, it means how many seats are in the 30th row? And we could just keep adding 5 every time, but that's a lot of work. So if we have the explicit formula, we just have to plug in one number and we get our answer. So that's what we use the explicit formula for. To calculate a sub 30, we're going to plug in a 30 for n and solve. So that's what I'll do, and we can plug either into Muna's equation or the original. I'll just use the original equation. Muna's is probably faster though. All right, so this is first term plus the difference n minus 1. Oops, I should put d here. right, so when we plugged in for this particular problem, we want a sub 30. The first term was 10. There were 10 seats in the first row. It's going up by 5 every time, so that's the common difference. And when we have a sub 30, all it means is plug in a 30 for n. So this will be 30 minus 1. And now I have numbers on this whole side, and I can just type that in. So 10 plus 5 parentheses, 30 minus 1, which is 29. If I plug that in, we can see that in the 30th row, there's 155 seats. So the explicit formula allows us to just plug in one number and then get the answer instead of adding 5 every time, like 30 times or 29 times. So we can write a sub 30. So again, I'm just doing shift underscore to get that equals, and it was 155 seats. Okay, so we are going to practice more plugging in, but first let's practice just like, can you recognize the formula? So it says, an amusement park season pass costs $25 for the first month, $10 for each additional month. Stacy thought this was a good deal and decided to pay for it. Which of the representations below model how much Stacy will be paying? All right, so we have two numbers here. 26 is the first term, and we're adding $10 a month, so that adding 10 is that common difference, or D. So let's take a look and figure out which one of these equations would work. So the first one, 26 is the starting value, and we're adding 10 every time, so that works. The second one doesn't because this is subtracting 10 every time. If we distribute, will we get any of these? So I'm going to write this down, and let's distribute like Muna did on the last problem and see if we get any of these same answers. Okay, so I'm going to distribute. Okay, so here's the distributing. We'll have 10n minus 10, and we'll add that to the 26 plus. Okay, so now, so we distributed. Let's combine like terms. So what this means is, you know, the y-intercept, we would go backwards 10. So really we would start at 16 because the first term is 26. The zero term would be 16. And we're adding 10 every time. So here's one way to write that. Another way to write that is, again, we're starting at 16 as the y-intercept. And 10 is the slope, so we can put it in terms of y and x as well. So any of these are also mean the same thing. So let's see if we have that. Okay, yes, we have that here. And we also have it right here. So many different representations of that problem. Okay, practice 2. Darby has agreed to donate $196 to Knoxville for its library. In addition, she will donate $3 for every book that a student or child that visits the library reads during the summer. The sequence shown represents the possible outcomes. So she starts with 196. A kid reads a book, she donates $3 more. A kid reads a book, she donates $3 more, and so on. So which one of these representations work? So again, the starting value is 196, and we're adding $3 every time, so this one would work. This is multiplying by -3, that wouldn't work. And then let's distribute and simplify. So again, we have a sub n equals 196 plus $3 every time. And again, what this does is it just shifts it back to the y-intercept. So we have 3n minus 3. So really what we're doing is we're going backwards 3 terms. So another way to write this is 193, which is the y-intercept, plus 3n. So you can also start at, if the zero term is 193, and add 3 every time. So let's look for that. So here it is, 193, we're adding 3 every time. We can also put it in terms of x, but again, if you do that, the y-intercept is 193 because the first term is 196. So several representations for that as well. Okay, so try this one. Emerson is a stingy donor. She originally donated $168 to Reeves Rogers for its library, but she can't stand a certain book series. Every time she sees a child reading a book from the series, she's going to take back $8 from her donation. So here's a list of terms. So every child that reads the book she doesn't like, she's taking back her $8. Which representations model this situation? So we're starting with 168, but this time we're subtracting 8 every time, so this one would work. And then if we go backwards 8, so really that's what this does. This 168 is the first term. So if we take 168, but then add $8, that would give us the y-intercept. So I'll show you that work right here. Write it down first. So a sub n equals 168 minus 8, n minus 1. Okay, so again, to simplify this, we can distribute. -8 times n is negative 8n. Negative 8 times negative 1 is plus 8. And then we'll add that to the original part of the equation. So notice here, to find the first term, instead of subtracting 8, we will add 8. So 168 plus 8 will give us 176 minus 8n. So here's another way to write the equation, or y equals 176 minus 8x, or f of x we could say. So either of these mean the same thing as that first one that we chose. So 176 minus 8x. All right, so there's again 3 equations that model that situation. Match the following tables with the explicit formulas that they represent. Not all choices will be used. All right, so I'm going to start with the table. All right, so this is skaters charged, looks like $20 more for each lesson, and we start at 60. So here, this would match, right? We're starting with 60. We're adding $20 more a lesson. We'll overlap that, put them together. All right, let's do this one next. All right, this one, again, is going up. Looks like $16 a month. Starts at 84. So here's 84 starting at 16 a month. Matched up. This one starts at 125, but we're losing $25 a week. All right, so losing 25. So it'd be this one right here. Okay. Okay, so now let's actually use the formula. It says find the 55th term of the sequence 8, 24, 40. Another way to find this is find a sub 55. Okay, so I'm going to show my work for this one. So we want a sub 55. We have 8, 24, 40, and so on. All right, so we need to figure out first term. So here's our first term is 8. Here's our second term, third term. And we got to figure out, what is this going up by every time? So let's start by subtracting 40 minus 24, and we get 16. Let's try 24 minus 8, and we get 16 as well. So we can see this is arithmetic, because if you add 16 every time, we get the next term. And again, to do that, all I did was take any term, divide by the term before it, and it worked for both of them. So we get 16 every time. Okay, so that's all the information that we need to write the formula. So to find the 55th term, we take our first term, which is 8. We're adding 16 every time. That's the common difference. And then n minus 1. But we know that here n is 55. So really I should have plugged in a 55 right here. And now we can just plug this in. So I will do 8 plus 16 parentheses, 55 minus 1. And the 55th number in this list would be 872. So that's a lot faster than trying to add 16 like 54 times. So there it is. The 55th term is 872. I'll just type in 872, and then you would submit your answer. All right, let's try another one. Dylan is starting a running plan to train for a race. In the first week of his running plan, Dylan will run 14 miles. The plan calls for Dylan to increase his weekly mileage by 3.5 miles every week. If Dylan sticks to the plan, how many miles would he be expected to run during his 10th week of training? All right, so again, I'm going to show my work for this one. So he wants the 10th week. He starts with 14 miles, and he's adding to that 3.5 miles per week. So times n minus 1, but we know what n is. We know it's 10 weeks, so I'm actually going to put a 10 in there, and now we can just type it in. So 14 plus 3.5 parentheses 10 minus 1, and on the 10th week, he would be running 45.5 miles. Oops, I put h sub 0. All right, that's a lot of running, Dylan. All right. Okay, so let's put that 45.5 miles. Oh. Okay, so we've completed the lesson. It's on arithmetic sequences. There's that formula you're going to use to find different terms of a sequence. You have to know about the first term and the common difference, and be able to identify which equation to use. So you can head to Delta Math and complete 5.2 explicit formula for arithmetic sequences for your assignment, and it's due our next synchronous class. So if you have questions, you can let me know during the asynchronous period or on Wednesday help time.